A clay tablet smaller than a paperback book sits behind climate-controlled glass in Columbia University's rare book and manuscript library. Its surface measures roughly 13 centimetres wide, 9 centimetres tall. The clay is the colour of dried river mud, which is exactly what it once was, pulled from the banks of the Euphrates over 700 years ago, shaped by hands we'll never know, impressed with a reed stylus by someone who understood mathematics in ways we're only beginning to comprehend. The tablet's catalogue number is Plimpton 322. If you could hold it, you'd feel its weight, substantial, dense, the compression of millennia. You'd notice immediately that its left edge is broken, sheared away at some point in its long journey from the ancient city of Larsa to this temperature-regulated room in Manhattan. Whatever was written in those missing columns is gone. And that absence might be the most important thing about it, because what remains, 4 columns of numbers arranged in 15 careful rows, inscribed in the wedge-shaped marks of cuneiform script, has rewritten our understanding of ancient mathematics 3 times in the last 80 years. Each generation of scholars who examined it found something their predecessors missed. Each interpretation suggested the Babylonians knew more than we thought possible, and each new reading raised the same uncomfortable question: where did this knowledge come from? The numbers themselves are precise, methodical, arranged in a pattern that only makes sense if you understand advanced mathematical relationships, the kind of relationships we don't teach until high school or university, the kind that require, according to every history textbook written before 1945, the Greeks to invent them more than 1,000 years after this tablet was fired in a Mesopotamian kiln. But here it sits, undeniably old, undeniably mathematical, undeniably precise. The story we've been told about the history of mathematics has a comfortable arc. Primitive counting evolved into basic arithmetic, which slowly, over centuries, developed into geometry, which eventually, through the genius of Greek philosophers, blossomed into advanced mathematics. A steady climb from ignorance to understanding, from simple to complex, from darkness to light. Plimpton 322 doesn't fit that story. Neither do the dozens of other tablets excavated from the ruins of Mesopotamian cities over the last century. They suggest something else, something that makes the standard narrative uncomfortable. They suggest the mathematics we credit to the Greeks might not have been invented at all. It might have been remembered. Before we go further, and this journey will take us from museum vaults to excavated schoolhouses, from ancient Larsa to scholars arguing in academic journals, tell me where you're listening from and what time it is where you are. This is a long exploration, meant to accompany you through quiet hours. Whether you're in Portland at midnight or Perth at dawn, the questions raised by this tablet cross all boundaries of time and space. Because what we're really asking is this: what if the mathematics that built our modern world wasn't discovered through slow, methodical progress, but recovered from something older? What if ancient scribes weren't inventing, but transcribing? What if they were preserving? The broken edge of Plimpton 322 mirrors the broken edge of our understanding. We can read what's there, we can analyse it, decode it, marvel at its sophistication, but we can't see what's missing. And perhaps what's missing matters most of all. This is not a story about aliens or Atlantis or mystical wisdom. This is a story about clay, reeds and numbers, about excavation, translation and scholarly debate, about what happens when the physical evidence refuses to conform to the timeline we've constructed, about what the Sumerians and their Babylonian inheritors actually recorded, and why 37 centuries later we're still trying to understand what they knew. The tablet sits in its case, silent and patient. It has waited this long, it will wait longer, but the numbers pressed into its surface 3,700 years ago haven't changed. Only our ability to read them has. Let's begin where every investigation must, with the moment of discovery, with the man who brought this tablet out of the Iraqi desert, and with the ancient city where it was made. A merchant of ancient secrets, Edgar James Banks stood in the ruins of Tel Senkere in the early years of the 20th century, supervising local workers as they carefully excavated through layers of compacted earth and broken brick. The Tel, an archaeological term for a mound built up over centuries of human habitation, rose from the flat Mesopotamian plain like a whale's back, breaching the surface of time itself. Beneath his feet lay Larsa, one of the great cities of the old Babylonian period. Abandoned for millennia, its ziggurats collapsed, its streets buried under the accumulated dust of 3,000 years. Banks was an unusual figure in the world of early archaeology. He held a doctorate from the University of Breslov and had worked on excavations at Besmaya, but he was also, fundamentally, a businessman. He dealt in antiquities. He understood that the clay tablets emerging from sites like Larsa had value, not just scholarly value, but monetary value. Universities and collectors in America and Europe were hungry for cuneiform tablets, for physical evidence of the biblical world, for anything that could illuminate the shadowy origins of civilization. The work at Tel Senkere was not a formal institutional excavation in the modern sense. Banks operated more as an entrepreneur of the past, hiring local labour, purchasing finds, acquiring tablets from other dealers and diggers. The archaeological standards of the early 1900s were, by contemporary measures, catastrophic. Context was often ignored, stratigraphy was poorly recorded, tablets were cleaned, handled, sometimes damaged in ways that would horrify modern conservators. But this was the era when the great museums were built, when the ancient Near East was being recovered from obscurity, when cuneiform was finally, after thousands of years of silence, being read again. At some point during his work around Larsa, the exact circumstances lost to inadequate record-keeping, Banks acquired a collection of tablets that included what would eventually be catalogued as Plimpton 322. He may have excavated it himself. It may have been purchased from local people who found it. The broken left edge suggests it might have been damaged in excavation or during the centuries it spent buried. We don't know. Banks' records, like the missing columns of the tablet itself, are incomplete. What we do know is that by 1922, Banks was back in the United States and he was selling tablets. Among his potential customers was George Arthur Plimpton, a successful New York publisher with a passion for the history of education and mathematics. Plimpton had built a remarkable personal collection of mathematical texts and educational materials spanning centuries. He understood that ancient Mesopotamian tablets represented the earliest known evidence of formal mathematical instruction. They fit his collecting focus perfectly. In 1922 or 1923, sources differ on the exact year, Banks sold 5 tablets to Plimpton for a total of $10. $10. The price seems absurd now, but in the early 1920s, cuneiform tablets were not yet recognized as the extraordinary documents they are. One of those 5 tablets was the object now known as Plimpton 322. Plimpton had no idea what he'd purchased. The tablet was catalogued and shelved with the rest of his collection. It sat there, its significance unrecognized, for more than 2 decades. Plimpton died in 1936, and his collection was bequeathed to Columbia University, where it became part of the Rare Books Library. Still, no one looked closely at tablet number 322. It was just one of thousands of cuneiform documents in collections across Europe and America, most of them receipts, contracts, administrative records, the mundane paperwork of ancient bureaucracy. But this tablet was different, and in 1945, someone finally noticed why. The story of Edgar Banks himself has an epilogue worth noting. He would later claim to be the inspiration for the character of Indiana Jones, a claim that contains more wishful thinking than truth, but isn't entirely baseless. He was, in his way, an adventurer. He excavated in Iraq during a time when such work required navigating Ottoman authorities, dealing with local tribal politics, and enduring the harsh conditions of the Mesopotamian climate. He brought back treasures, he sold them, he moved on. Whether we judge him by modern archaeological standards, which he violates spectacularly, or by the standards of his own era, The fact remains, without Banks, Plimpton 322 would still be buried at Telsinkere. Without his commercial instinct for acquiring tablets, without Plimpton's passion for mathematical history, without Columbia's commitment to preserving donated collections, the tablet might have stayed in the ground forever, or crumbled to dust in some Baghdad bazaar. This is how knowledge survives, through chance, commerce, and collecting, through dealers and donors and institutions that archive what they don't yet understand. Banks didn't know he was handling one of the most important mathematical documents in human history. Plimpton didn't know either. The tablet sat in New York for 23 years before anyone realised what it was. This raises an obvious question. How many other tablets like Plimpton 322 have been lost? How many were destroyed during excavation? How many were purchased by collectors who didn't donate them to institutions, so they ended up in private hands, their contents unknown to scholarship? How many are still buried at Tel Senkara and other sites across Iraq, waiting for excavators with better methods and different questions? The mathematics preserved on Plimpton 322 survived, but barely, by luck, by accident, through a chain of custody that could have broken at any point if Banks had excavated a metre to the left, if Plimpton had spent his $10 elsewhere, if Columbia had refused the collection or disposed of it during renovations. And perhaps that's the first lesson of this tablet, the fragility of knowledge itself, how easily it disappears, how much can be lost in a single generation, a single fire, a single decision not to preserve something whose value hasn't yet been recognised. The tablet came from Lhasa. To understand what it represents, we need to understand that city, not the ruined Banks excavated, but the living city where someone pressed these numbers into wet clay 3,700 years ago. The city that calculated the heavens. Lhasa was old even when Plimpton 322 was made. The city's origins reach back to the early dynastic period of Mesopotamia before 2500 BC, but its golden age came during the Isin Lhasa period and into the Old Babylonian period, roughly 2000 to 1600 BC. This was when Lhasa controlled significant territories in southern Mesopotamia, when its kings built monumental architecture, when its scribal schools produced the mathematical tablets that would perplex scholars 3,000 years later. The city occupied a strategic position on the ancient course of the Euphrates River, in what is now southern Iraq, about halfway between the modern cities of Nasiriyah and Basra. In antiquity, this region was the heartland of Sumerian civilization, the place where writing itself was invented around 3200 BC. By the Old Babylonian period, the Sumerian language was no longer spoken. It had been replaced by Akkadian, but Sumerian remained the language of scholarship, of mathematics, of sacred texts. Scribes learned it the way European scholars learned Latin, as the language of knowledge itself. Lhasa's economy was built on agriculture. The fertile soil between the rivers, irrigated by an elaborate canal system, produced barley and dates in abundance, but its intellectual life was built on something else, the need to manage complexity. Irrigation systems required surveying, water distribution needed accounting, agricultural yields required calculation, temple administrators tracked offerings and distributions, long-distance trade required standardized measures and conversion between different systems. The calendar had to be maintained by astronomical observation to ensure religious festivals fell at the correct times. All of this required mathematics, not simple addition and subtraction, but sophisticated calculation. Mesopotamian scribes developed multiplication tables, tables of reciprocals for division, tables of squares and square roots, methods for solving quadratic equations. They calculated compound interest. They computed areas of irregular fields. They predicted lunar eclipses with remarkable accuracy. The astronomical work is particularly significant. Mesopotamian astronomers tracked the movements of the moon, the sun, and the visible planets with obsessive precision, recording their observations on tablets that accumulated into vast databases spanning centuries. They recognized patterns, the Saros cycle of eclipses, the periodicities of planetary motion. They understood that mathematics could model the heavens. This connection between mathematics and astronomy runs through all of Mesopotamian intellectual culture. The sexagesimal system, base 60, that the Sumerians developed was perfectly suited to astronomical calculation. The number 60 is highly divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. This made it ideal for dealing with fractions, for dividing circles into degrees, for measuring time. We still use Sumerian base 60 today, 60 seconds in a minute, 60 minutes in an hour, 360 degrees in a circle. These aren't arbitrary. They're the direct inheritance of the mathematical system developed in cities like Lhasa. But here's what makes Lhasa and its contemporary cities unusual. The sophistication of the mathematics appears suddenly fully formed. We don't see a gradual development from simple to complex. The earliest mathematical tablets we have, from the Ur-3 period, just before the Old Babylonian era, already demonstrate advanced techniques. It's as if the system was imported wholesale, not invented gradually. Scholars usually attribute this to the genius of Mesopotamian scribes, to the practical demands of administration and astronomy driving innovation. And certainly the scribes of Lhasa were trained professionals, spending years in scribal schools mastering cuneiform, memorizing tables, solving practice problems. We have hundreds of school tablets, student exercises, practice multiplication tables, problems worked out in a teacher's hand with a student's incorrect attempt scratched below. But the training texts themselves are telling. They don't teach the fundamentals of why the mathematics works. They teach procedures. Memorize these tables, follow these steps, apply this algorithm. It's algorithmic, procedural knowledge, the kind of knowledge you transmit, not the kind you develop from first principles. Contrast this with Greek mathematics as we know it from Euclid. The Elements doesn't just give you geometric facts, it proves them from axioms. It builds a logical structure where each theorem depends on previous theorems, all the way back to definitions and postulates. It's mathematics as philosophy, as logical argument, as truth-seeking. Mesopotamian mathematics isn't like that. It's mathematics as technology, as tools, as methods that work. There's no explanation of why they work. A scribe learns that to find the area of a circular field, you multiply the square of the circumference by a specific constant. Does the scribe understand why? The tablets don't say. The method works. That's sufficient. This has always struck historians as oddly modern. Our high school students learn the quadratic formula the same way, memorize it, apply it, don't worry about the derivation unless you're taking advanced math. It's practical, efficient, and it works. But it also suggests the knowledge might be older than the teaching tradition we can trace. Lhasa produced many such tablets, mathematical problem texts, astronomical records, tables of every kind. The city was a centre of learning, attracting scribes from across Mesopotamia, training new generations in the techniques that had been preserved, that word again, for centuries. When Hammurabi of Babylon conquered Lhasa in 1762 BC, the city's political power ended, but its intellectual traditions continued. The mathematics didn't disappear. It was carried to other cities, Babylon, Nippur, where new generations of scribes copied the old tablets, solved the old problems, transmitted the knowledge forward. And at some point in the 18th century BC, a scribe in Lhasa took a lump of clay, formed it into a tablet, and carefully inscribed what we now call Plimpton 322. Why? For what purpose? As a reference table, a teaching tool, a demonstration of skill? We don't know. The tablet doesn't say. Like so much of what we've recovered from Mesopotamia, it presents information without commentary, data without interpretation, knowledge without context. It simply exists. 4 columns of numbers, 15 rows, and a broken edge where more knowledge might have been recorded. The city that made it is gone. Tel Senkere today is a barren mound in a flat landscape, visited occasionally by archaeologists, avoided by the political chaos that has engulfed Iraq repeatedly over the last century. The ziggurats are dust. The canals are dry. The scribal schools are collapsed piles of mud brick. But the mathematics survives, transferred from wet clay to fired tablet, from buried tablet to museum collection, from cuneiform to modern notation, from ancient Lhasa to Columbia University in New York. The question is, what exactly survives? What are we looking at when we examine Plimpton 322? To answer that, we need to look at the tablet itself, not at the stories of its discovery or the city that produced it, but at the actual numbers impressed into its surface 3,700 years ago. 4 columns, 15 rows, infinite questions. The tablet before us measures 12.7 centimetres in width and 8.8 centimetres in height. Its broken left edge is irregular, suggesting that at least one column, possibly 2, is missing. What remains is divided into 4 columns, separated by vertical rulings scratched into the clay. 15 horizontal rows organise the content. Each cell contains a number written in cuneiform sexagesimal notation, base 60. If you're not familiar with base 60, it works like this, where we have a ones place, a tens place, a hundreds place, they had a ones place, a 60s place, a 3600s place. A number like 1,059,015 in their notation would mean 13600 plus 5960 plus 01 plus 1560, or in decimal 7140.25. The challenge for modern readers is that the cuneiform script doesn't always indicate place value clearly. Context determines whether a symbol means 2 or 120 or 260. This ambiguity has led to some misreadings over the years. The leftmost surviving column, what we'll call column I, contains numbers that decrease as you read down the rows. The first entry is approximately 1.9834027 in decimal. The last is approximately 1.3871605. These aren't whole numbers in any obvious sense, and their pattern isn't immediately clear. Column 2 contains larger numbers, whole numbers ranging from 169 to 481. These at least are straightforward. Column 3 contains even larger numbers, from 2291 to 8161, also whole numbers. Column 4, the rightmost column, contains what appears to be a counting sequence, the numbers 1 through 15, labelling each row. At first glance, this looks like a table. Row identifies in column 4 3 columns of data, organised in descending order. But a table of what? The breakthrough came in 1945, when mathematician Otto Neugebauer and his assistant Abraham Sachs examined the tablet as part of their comprehensive study of Mesopotamian mathematical texts. They recognised something remarkable. The numbers in columns the 2 and the 3rd are related by the Pythagorean theorem. Specifically, if you call the number in column 2 b and the number in column 3rd, then there exists a whole number as such that a plus b deduct c. In other words, RB form a Pythagorean triple, the sides of a right triangle with integer lengths. Look at row 1. Column 2 gives 119. Column 3rd gives 169. Is there a whole number as such that a plus 119, 169?
Yes, 120 plus 119 plus 14400 plus 44161 plus 28561 is 169. The triple is 120, 119, 169. Row 2, column 2 is 3367, column 3 is 4825, 3456 plus 3367 slots 4825. Row 3, column 2 is 4601, column 3 is 6456, 4800 plus 4601 so 6649. Every row follows this pattern. Each entry represents a Pythagorean triple.
The tablet lists 15 such triples, all with specific mathematical properties. Now, Pythagorean triples were not unknown in the ancient world. The simplest one, 345, appears in multiple cultures and could be discovered empirically by anyone working with ropes and surveying. But Plimpton 322 isn't listing simple triples, it's listing sophisticated ones, large numbers, specific selections. And here's where it gets strange. The triples are ordered by the value in column myth, which Neugebauer and Sachs recognised as sec, the secant squared of the angle opposite the side of length A. In modern trigonometric terms, column fern tracks sec lec CB as decreases from about 45 to 31. This is advanced, this is trigonometry, or at least something functionally equivalent to trigonometry. But trigonometry, the mathematics of triangles, angles and circles, was supposed to be invented by the Greeks, specifically by Hipparchus of Rhodes around 140 BC. That's 1500 years after Plimpton 322 was made. Neugebauer's interpretation caused immediate excitement and has generated debate ever since. Because if this tablet is trigonometry, then the history of mathematics needs revision. If the Babylonians had trigonometric tables in 1800 BC, then the Greeks didn't invent the field, they rediscovered it, or learned it from earlier sources, or developed it independently along parallel lines. But there's another layer. Column Y, the column with the decreasing values, contains 5-digit sexagesimal numbers computed to extraordinary precision. These aren't approximations. They're exact values, calculated correctly to multiple decimal places or sexagesimal places in their notation. The computational skill required to generate these numbers without modern calculators is formidable. Mesopotamian scribes used tables, multiplication tables, reciprocal tables, tables of squares to perform calculations. But even with tables, the arithmetic needed to produce Plimpton 322 would have required hours of careful work, multiple steps, and error-checking procedures we can only guess at. Why? Why invest that much effort? Why create a table of 15 Pythagorean triples ordered by a specific trigonometric function computed to high precision? Neugebauer suggested it was a reference table, perhaps used for surveying or astronomical calculation, a practical tool for professionals who needed to solve problems involving right triangles. But there are problems with this interpretation. The triples listed on Plimpton 322 are not practical. They involve enormous numbers, 12709, 3500, 118541 is one of them, that have no obvious application in real-world surveying. No one measures a field and gets 13,500 units on a side. The numbers are mathematically elegant, but practically useless. Which raises another possibility. What if this isn't a practical reference table? What if it's something else? This is where the broken left edge becomes crucial. Scholars have attempted to reconstruct what the missing columns might have contained. The most common reconstruction suggests column A, the leftmost missing column, contained the values, the short sides of the right triangles. This would make sense. A complete table would list all 3 sides of each triangle. If that's correct, then the tablet once contained a complete listing, ABC, and the computed sec for 15 specific Pythagorean triples. But why these 15? There are infinitely many Pythagorean triples. Why this selection? Mathematicians have analysed the pattern. The triples on Plimpton 322 are generated by a specific algorithm using pairs of integers p and q, where p.q using the formula adjoc.pq, b.2pq, c.p plus q. This formula generates all primitive Pythagorean triples, triples where a, b, and c share no common factors. The tablet uses pairs, q, where p ranges from 12 down to 5, and q is chosen to keep the resulting triple within certain bounds. This is systematic, algorithmic. It suggests the scribe who made this tablet understood the deep structure of Pythagorean triples, knew how to generate them at will, and selected a specific sequence for a specific purpose. That purpose remains mysterious. The fourth column, the row numbers 1 through 15, seems like an obvious organising feature, but in the cuneiform script used on the tablet, the numbers are written in an unusual way. Some scholars have suggested these aren't row numbers at all, but rather tags or identifiers relating to some other organisational scheme we don't understand. Every detail of Plimpton 322 invites questions. Every answer generates new mysteries. The more precisely we can read the tablet, the less certain we become about what it means. And we haven't yet addressed the central question. How did they know to do this? Where did the algorithm come from? Why does a tablet from 1800 BC demonstrate mathematical sophistication that we attribute to civilizations more than a millennium later? Before we can answer that, we need to step back and understand how we can read the tablet at all. We need to understand cuneiform, the writing system that preserved this knowledge, and the scholars who unlocked it after 3,000 years of silence. The language of wedges. For more than 3,000 years, cuneiform was unreadable, the script that had recorded laws, epics, prayers, receipts, astronomical observations, and mathematical tables, the script used across Mesopotamia, Anatolia, Persia, and the Levant for 3 millennia, became extinct sometime in the 1st century AD. The last datable cuneiform tablet was written in 75 AD. After that, silence. The knowledge inscribed on hundreds of thousands of clay tablets was locked away, inaccessible, forgotten. The tablets themselves were durable. Fired clay or sun-dried clay buried in the dry soils of the Middle East can survive for millennia, but they might as well have been blank. No one could read them. The rediscovery began in the 19th century with the work of European scholars and explorers who encountered mysterious inscriptions on ancient monuments. The Behistun inscription, a massive trilingual text carved into a cliff face in western Iran by the Persian king Darius I around 500 BC, proved to be the key. It contained the same text in 3 scripts: Old Persian, Elamite, and Babylonian. By 1857, the Babylonian section had been deciphered, and scholars could finally read cuneiform again. The process took decades. Cuneiform isn't a single language, it's a writing system adapted for multiple languages, primarily Sumerian and Akkadian. Sumerian, a language isolate with no known relatives, was already dead when Plimpton 322 was made, but it remained the language of scholarship. Akkadian, a Semitic language, was the spoken language of Babylonia during the Old Babylonian period. Scribes had to master both. The script itself is complex. Each cuneiform sign can represent a syllable, a word, or a semantic determinative, a marker that indicates what category a following word belongs to. Context determines meaning. There's ambiguity built into the system, requiring educated readers who understand conventions and context. Mathematical texts introduced additional challenges. Mesopotamian scribes used specialized terminology, abbreviated notations, and conventions that aren't explicitly explained in the texts themselves. Early translators struggled to understand what they were reading. Was this a multiplication table or a reciprocal table? Was this number meant to represent area, length, or volume? Was this symbol a numeral or a word? Otto Neugebauer, working in the 1930s and 1940s, was among the first scholars to systematically study Mesopotamian mathematical texts. He brought mathematical training to the task of translation, recognizing patterns and procedures that purely linguistic scholars might miss. His 1945 work with Abraham Sachs, Mathematical Cuneiform Texts, remains foundational. When they examined Plimpton 322, they had the advantage of decades of work on similar tablets. They knew how Babylonian numerals worked. They understood sexagesimal notation. They recognized tables when they saw them. But even with that expertise, Plimpton 322 resisted immediate interpretation. The sexagesimal place value system is particularly challenging. Our decimal system has a clear separator, the decimal point, that distinguishes 25.5 from 255 from 2.55. Cuneiform sexagesimal notation has no such separator. A symbol group representing 25 could mean 260 plus 5, 125, or 2 plus 560, 2.0833, or 23600 plus 560, 7500. You have to infer place value from context. Neugebauer and Sachs, analysing the numbers in columns 2 and the third, noticed they were perfect Pythagorean pairs when interpreted with specific place values. This wasn't random. The numbers were too precisely chosen, too systematically organised. Once they recognised the pattern, column the first became interpretable. It tracked CB, the squared ratio of the hypotenuse to one leg. This interpretation wasn't universally accepted immediately. Some scholars questioned whether the Babylonians would have thought in trigonometric terms. Trigonometry, as the Greeks developed it, is based on angles and circles, concepts that require geometric visualization and the concept of angle measure. Did the Babylonians have that? The answer is, sort of. They didn't have degrees in the modern sense, but they divided circles into 360 parts, a number derived from the sexagesimal system 660. They tracked celestial motions, which are fundamentally angular. They understood ratios and proportions. Whether they conceptualized these as angles in the Greek sense is debatable, but they clearly understood the relationships. Another challenge, the Babylonian mathematical tradition doesn't include proofs. There are no theorems, no lemmas, no demonstrations that relationships are universally true. There are only procedures and tables. This makes it difficult to know what they understood conceptually versus what they knew procedurally. For example, did the Babylonians know that a plus b tuple c is always true for right triangles as a proven theorem? Or did they know empirically from surveying and construction that certain number triples have this property? The tablets don't say. They give examples, algorithms, computational methods. They don't justify them. This procedural character is one of the most distinctive features of Mesopotamian mathematics. It feels modern in some ways, algorithmic, computational, but utterly foreign in others. There's no mathematical philosophy, no questioning of foundations, no attempt to prove results from first principles, and yet the results are correct, the algorithms work, the tables are accurate, the mathematics is sophisticated, even if it's not expressed in the way we're accustomed to since Euclid. Translating Plimpton 322 required not just linguistic skill, but mathematical insight. Neugebauer had to recognise what kind of mathematics was being done, what relationships the numbers represented, what the overall structure aimed to achieve. It's detective work, finding patterns in fragmentary evidence, reconstructing intention from bare facts, inferring purpose from structure. And there's another layer of difficulty, scribal errors. Ancient scribes made mistakes. They copied numbers incorrectly. They transposed digits. They miscalculated. Modern scholars examining a mathematical tablet have to decide, is this strange number a sophisticated mathematical idea we don't understand, or is it a copying error? Usually, you can tell by checking whether the number fits the pattern. If 15 entries follow a clear mathematical rule and one doesn't, it's probably an error. But if you don't yet understand the pattern, you can't identify the errors, which means you can't correctly interpret the pattern. Neugebauer's interpretation of Plimpton 322 was brilliant detective work. He saw the Pythagorean triples, he saw the ordering principle, he saw the underlying trigonometric structure. His reading has held up for nearly 80 years, though it's been refined and debated continuously. But here's what strikes me most. The fact that the tablet could be read at all. The chain of improbable preservation that starts with a scribe in Lhasa forming wet clay and ends with Neugebauer in 1940s America deciphering it. The hundreds of scholars across 2 centuries who slowly unlocked cuneiform, who built lexicons and grammar guides, who published transliterations and translations, who created the infrastructure of knowledge that made Neugebauer's work possible. Without that infrastructure, Plimpton 322 would be meaningless scratches on a clay rectangle. The information would exist, physically present, chemically stable, but it would be inaccessible. Data without interpretation is just noise. This is worth sitting with, how fragile knowledge is, how dependent on continuous transmission. The Babylonians had sophisticated mathematics, but when the culture that could read their script died out, the knowledge became inaccessible. It took 3,000 years to recover it, and we've recovered only a fraction. Tens of thousands of tablets remain untranslated in museum storage, awaiting scholars' with time and funding. How much have we lost permanently? How many tablets were destroyed, weathered away, recycled for clay, or simply never excavated? What percentage of Mesopotamian intellectual achievement survives? We don't know. We can't know. We have what we have. Fragments, samples, glimpses. We reconstruct a civilization from scraps. But the scraps we have are extraordinary. And Plimpton 322, once Neugebauer decoded it, proved more extraordinary than almost anyone had imagined. Neugebauer's revelation. The year was 1945. The Second World War had just ended. Otto Neugebauer, an Austrian mathematician who had fled Nazi Germany in the 1930s, was teaching at Brown University in Providence, Rhode Island. He had spent much of the previous decade studying Mesopotamian astronomy and mathematics, compiling and translating cuneiform tablets from collections around the world. Neugebauer approached ancient mathematics not as a historian of ideas, but as a mathematician examining mathematical work. He wasn't primarily interested in cultural context or the broader sweep of civilization. He wanted to know what mathematics did they do and how did they do it. This approach was relatively new. Earlier scholars had treated ancient mathematics as a curiosity, primitive precursors to Greek genius. Neugebauer took it seriously on its own terms. He recognized that Babylonian mathematics was sophisticated, internally consistent, and in some ways more practical than Greek mathematics. When he and Abraham Sachs examined the tablets in Columbia's Plimpton collection, tablet 322 immediately stood out. The numbers were too large, too precise, too carefully arranged to be simple bookkeeping. This was mathematics for its own sake, or for some purpose that required high-level computation. Neugebauer's first step was to convert the cuneiform sexagesimal numbers into decimal notation and see if patterns emerged. When he did, he recognized the Pythagorean relationships immediately. A Pythagorean triple is any set of three positive integers, a BC, such that a plus B does C. The most famous is 3, 4, 5, 3 plus 4, 9 plus 16, 25, core 5. But there are infinitely many such triples. You can generate them systematically using the formula I mentioned earlier. Pick two integers p juxt q, then set a juxt pq, b juxt 2pq, c juxt p plus q. Plimpton 322, Neugebauer realized, listed the b and c values for 15 such triples. The a values weren't explicitly shown. They were presumably in the missing left column, but Neugebauer could calculate them by solving a Douglas CB. Why list Pythagorean triples? Because they represent right triangles with integer sides. If you're surveying land, designing buildings, or doing any geometric calculation involving right angles, these triples are useful. You can lay out a perfect right angle using a rope marked in the ratio 3045. Scale up to larger triples and you can handle bigger projects. But Neugebauer noticed something else. The triples were ordered in a specific way. Row 1 had the triple where the angle opposite side A was closest to 45. Each subsequent row decreased that angle slightly. By row 15, the angle was down to about 31. This ordering suggested the tablet wasn't just a list of useful triples, it was a table organized by angle, a trigonometric table. Trigonometry is the study of relationships between angles and sides in triangles. Modern trigonometry uses sin, cosine, tangent, and related functions. These functions take an angle as input and output a ratio. For example, in a right triangle, sin 6 opposite / hypotenuse. The Greeks developed trigonometry around 140 BC, with Hipparchus of Rhodes often credited as the founder. He created tables of chord lengths for circles, which is geometrically equivalent to a table of sin values. This work supported astronomy. Tracking the positions of celestial bodies requires sophisticated angular calculations. But Plimpton 322 predates Hipparchus by 1500 years. Neugebauer's interpretation was that the Babylonians had developed a form of trigonometry based not on sine and cosine, but on secant and tangent, functions related to ratios of triangle sides. Column first, he argued, tracked sect, the square of the secant function. This was revolutionary. It meant the Babylonians had trigonometry, practical functional trigonometry, over a millennium before the Greeks. The standard narrative of mathematical history, which placed the Greeks as the inventors of advanced mathematics, needed revision. Neugebauer published his findings in 1945 in Mathematical Cuneiform Texts, co-authored with Sachs. The academic community took notice. Here was physical evidence, a fired clay tablet, undeniably ancient, that demonstrated advanced mathematical concepts far earlier than previously thought. But not everyone agreed with Neugebauer's interpretation. Scholarly debate began almost immediately. Some argued that the tablet's purpose wasn't trigonometry, but algebra. The Babylonians were skilled algebraists, solving quadratic and even some cubic equations using systematic methods. Perhaps Plimpton 322 was a table of solutions to a particular class of algebraic problems, and the apparent trigonometric structure was coincidental. Others pointed out that the triples listed on the tablet are wildly impractical. The largest triple is 12709, 13500, 18541, numbers far too large for any real-world surveying or construction application. If this was a practical reference table, why not use smaller, more manageable numbers? And there was the deeper question: did the Babylonians think in terms of angles and trigonometric functions? They had no word for angle in the Greek sense. Their geometry was more computational than conceptual. They solved problems, they didn't prove theorems. Neugebauer's response was pragmatic. Whatever the Babylonians called it, whatever conceptual framework they used, the mathematics on Plimpton 322 is functionally equivalent to a trigonometric table. The fact that they organised right triangles by the ratio of hypotenuse to base, which corresponds to the secant function, demonstrates they understood angular relationships, even if they express them differently than we do. For decades, Neugebauer's interpretation was the scholarly consensus. Textbooks on the history of mathematics cited Plimpton 322 as evidence of Babylonian trigonometry. The tablet became famous, one of the most discussed mathematical artifacts from the ancient world. But consensus doesn't mean certainty, and in 2002, a scholar named Eleanor Robson published an alternative interpretation that challenged Neugebauer's view and reignited debate. Before we get to that, though, we need to establish one more piece of context. The Babylonians were not the only ancient culture with knowledge of the Pythagorean theorem. In fact, they weren't even the earliest. The problem Pythagoras didn't solve first. The theorem we call Pythagorean, that in a right triangle the square of the hypotenuse equals the sum of the squares of the other two sides, was not discovered by Pythagoras. He probably never wrote it down. He may never have proven it. The attribution to Pythagoras comes from Greek tradition written centuries after his death by authors who routinely credited famous philosophers with ideas that developed gradually across generations. Pythagoras lived around 570 to 495 BC. Plimpton 322 was made around 1800 BC. The theorem was known in Mesopotamia at least 1300 years before Pythagoras was born. And we can prove it because we have other tablets. Consider IM 67118, a clay tablet in the Iraq Museum in Baghdad. It's dated to approximately 1770 BC, roughly contemporary with Plimpton 322. The tablet shows a geometric problem. Given a rectangle with specific area and diagonal, find the sides. The solution uses the Pythagorean theorem explicitly, not as a theorem requiring proof, but as a known relationship applied to solve the problem. The mathematics is straightforward. If the rectangle has sides A and B, area A dux ab, and diagonal deducts are plus b, then you can set up the equations and solve for A and B. The tablet doesn't explain why deducts a plus b, it just uses it. This suggests the relationship was well established, standard knowledge for any trained scribe. Or consider YBC 7289, another famous tablet from the Yale Babylonian collection. It's a round school tablet showing a square with its diagonals drawn. Inscribed on it are sexagesimal numbers representing the side of the square, the diagonal, and the ratio diagonal/side, which is the square root of 2. The approximation given is 124.5110 in sexagesimal, which converts to 1.41421.296 in decimal. The actual value of 2 is 1.41421356. They got it right to 5 decimal places. This is not accidental, this is computation using known algorithms. The Babylonians had methods for approximating square roots, iterative procedures that converged on accurate values. They applied these methods routinely. So by 1800 BC, Mesopotamian mathematicians understood the Pythagorean relationship for right triangles, how to generate Pythagorean triples systematically, how to compute square roots accurately, how to solve quadratic equations involving these relationships. All of this is documented, verified, undeniable. But it gets more interesting. Cross the ancient world to the Indian subcontinent. In India, geometric and mathematical knowledge was preserved in texts called the Shulba Sutras, literally rope sutras, instructions for constructing ritual fire altars using measured ropes. The oldest of these, the Bodhyayana Shulba Sutra, dates to approximately 800 BC, still earlier than Pythagoras. It contains an explicit statement of the Pythagorean theorem: the diagonal of a rectangle produces by itself both the areas which the two sides of the rectangle produce separately, in modern notation d∛A plus b. The Bodhyayana Shulba Sutra also includes approximations for 2, methods for doubling the area of a square, constructions for transforming circles into squares of equal area, and other advanced geometric procedures. The mathematics is practical, it's about ritual construction, but it's sophisticated. Now, the relationship between Indian and Mesopotamian mathematics is unclear. Did ideas travel along trade routes? Was there a common ancestor civilization from which both inherited knowledge, or did both cultures discover the same relationships independently? Historian Abraham Seidenberg, analysing the geometric knowledge in both traditions, argued in the 1960s that the similarities are too specific to be coincidental. He suggested that either Old Babylonia got the theorem from India, or Old Babylonia and India got it from a third source. That third source, if it existed, would have to be earlier than both, pushing the origins of advanced mathematics back even further. This is speculative, and most historians are uncomfortable with it. The standard view is that mathematics develops in response to practical needs, surveying, astronomy, commerce, and that similar needs produce similar solutions independently. Parallels don't prove contact. But the parallels are striking. Both the Mesopotamian and Indian traditions understand the Pythagorean relationship, use it for practical geometric construction, express mathematical knowledge procedurally as algorithms, not proof, transmit knowledge through scribal/priestly educational systems, preserve knowledge in durable media tablets in Mesopotamia, memorized oral transmission later written in India. And both traditions describe their mathematical knowledge as inherited, not discovered. Mesopotamian mathematical texts are anonymous. We don't know who created them. They're presented as standard knowledge, part of the scribal curriculum, without attribution to individual inventors. Indian texts attribute geometric knowledge to ancient rishis, implying it was received from earlier tradition. This contrasts sharply with Greek mathematics, where individual mathematicians are named, credited, and celebrated. Thales, Pythagoras, Euclid, Archimedes. We know their names, or at least names tradition assigned to specific achievements. Greek mathematics presents itself as discovery, as individual genius advancing knowledge. Mesopotamian and Indian mathematics present themselves as transmission, as preservation, as maintaining what was known. This difference in self-presentation doesn't prove anything about actual origins, but it's suggestive. It hints that the Greeks saw themselves as innovators, while earlier cultures saw themselves as custodians. What if they were both right? What if the Greeks innovated within a framework they inherited, a framework that included the Pythagorean theorem, sexagesimal mathematics, and sophisticated geometric relationships? The evidence from tablets like IM 67118, YBC 7289, and of course Plimpton 322 makes one thing clear. By 1800 BC, the mathematical knowledge existed. It was sophisticated, systematic, and widely taught. The question isn't whether the Babylonians knew advanced mathematics. They demonstrably did. The question is, where did they learn it? To approach that question, we need to understand not just what the tablets contain, but how that knowledge was transmitted. We need to enter the scribal schools, where young students spent years learning to read, write, and calculate. We need to visit the tablet house, the schoolhouse in House F. In January 1952, archaeologists from the University of Pennsylvania and the University of Chicago began excavating a residential area in the ancient city of Nippur, about 150 kilometers southeast of modern Baghdad. Nippur was never a political capital, but it was the religious heart of Mesopotamia, home to the temple of Enlil, the chief deity of the Sumerian pantheon. More importantly for our purposes, Nippur was a major centre of scribal education. The excavation team, led by Donald McCown, uncovered a neighbourhood of private houses from the Old Babylonian period, around 1800 BC, the same era as Plimpton 322. One house in particular, designated House F, yielded an extraordinary find, over 1,400 clay tablets, most of them school texts. House F was a scribal school. The Aduba, as the Sumerians called it, the tablet house. The tablets found in House F give us a direct window into ancient education. We can see what students learned, in what order, and how their training progressed from basic literacy to advanced mathematics. We can identify practice tablets, where a teacher wrote a model text on one side and the student attempted to copy it on the other. We can see mistakes, corrections, partial exercises, and completed masterworks. The curriculum was rigorous. Students began by learning individual cuneiform signs, practicing each one repeatedly until they could form it precisely. Then they learned sign combinations, syllables, whole words. They memorized lexical lists, long compilations of words organized by semantic category, types of trees, types of stones, types of fish. This built vocabulary and familiarity with the writing system simultaneously. Once students could read and write fluently, they progressed to literary texts. They copied Sumerian proverbs, myths, hymns. Remember, Sumerian was a dead language by this period, no one spoke it at home, but it was the language of scholarship, the language of the sacred texts, the language that connected the old Babylonian scribes to their Sumerian predecessors, who had invented writing 2,000 years earlier. And then came mathematics. The mathematical tablets from House F include multiplication tables for numbers from 1 to 20, 30, 40, and 50, tables of reciprocals used for vision, tables of squares and square roots, problems involving areas of fields, volumes of granaries, distributions of goods, geometric problems requiring calculation of diagonals, circumferences, areas. These weren't textbooks in our sense. There were no explanations, no worked examples showing why procedures worked. They were reference tables and practice problems. Students memorized the tables and learned to apply standard algorithms. Consider a multiplication table. A student would practice writing out the multiples of, say, 9, 1 9 49, 2 9 Cla 18, 3 9 Cla 27, and so on up to 29 Clas 180, but not in base 10 notation, in sexagesimal with cuneiform numbers, in a specific formulaic layout. and students would do this for dozens of numbers, building a mental library of products they could recall instantly, or reciprocal tables. Division in sexagesimal isn't straightforward, so instead of dividing by a number, you multiply by its reciprocal. The reciprocal of 2 is 30, because 2 30 ducks 60 ducks 1 in base 60 place value. The reciprocal of 5 is 12. The reciprocal of 8 is 737.5. Students memorize these. But here's the problem. Not all numbers have finite sexagesimal reciprocals. The reciprocal of 7, for example, is 08 million, 34 millions, 17, 834,017, repeating forever. The Babylonians called these unresolvable numbers and avoided them when possible. This is why the Pythagorean triples on Plimpton 322 use specific P and Q values. They're chosen to ensure all calculations involve only resolvable numbers with finite reciprocals. This algorithmic approach, memorize procedures, avoid problematic cases, apply standardized methods, characterizes Babylonian mathematics. It's efficient, practical, and trainable. You can teach it to students without requiring them to understand deep theoretical foundations. But here's what strikes me about House F, the sheer volume of mathematical education. Over 1,400 tablets, and a significant fraction, are mathematical. These aren't administrative records or literary texts. They're teaching materials, practice exercises, demonstration tablets. Why was mathematics so central to scribal education? The practical answer is that scribes needed mathematics for their professional work. Temple administrators calculated offerings and distributions, royal bureaucrats assessed taxes, managed labour, planned construction projects, merchants computed prices, interest rates, and exchange rates between different currencies and measurement systems. All of this required fluent calculation. But the mathematics taught in schools like House F goes beyond practical need. Plimpton 322, for instance, serves no obvious administrative purpose. The problems on many mathematical tablets are artificial, calculate the dimensions of a pile of grain shaped as a complex geometric solid, or find the interest on a loan compounded over an absurd time period. These are exercises designed to test computational skill, not solve real problems. The Mesopotamian scribal class valued mathematical competence for its own sake, as a mark of intellectual sophistication. A well-trained scribe could solve complex problems, manipulate large numbers, work with precision. This was a form of cultural capital, a demonstration of education and capability, and the knowledge was standardized. The same multiplication tables appear at Nippur, at Ur, at Lhasa, at Babylon. The same algorithms are used across centuries and across cities. This isn't decentralized folk mathematics, invented and reinvented locally. This is a unified curriculum transmitted through a formalized educational system preserved across generations. The preservation mechanism was physical, clay tablets. A tablet, once fired, or even just thoroughly dried, can last millennia if buried in the right condition. So when a student mastered a multiplication table, the practice tablet often ended up discarded in a pile that eventually became part of the house's foundation or was used as fill. Centuries later, archaeologists dig through that fill and recover the tablets. This is why we have such rich documentation of Mesopotamian mathematics. The writing medium was durable, the culture was prolific in producing tablets, and the dry climate of southern Iraq preserved them. If Mesopotamians had used papyrus or parchment like the Egyptians or Greeks, far less would have survived. But the preservation was also cultural. Teachers teaching students, teaching the next generation of students. The curriculum at House F in 1800 BC included Sumerian literary texts composed 500 years earlier. Those texts were copied, studied, memorized, passed down. The mathematics was the same. Algorithms developed generations before were taught as standard methods, without modification, without attribution. This transmission system was remarkably stable. Mathematical methods documented in tablets from 2000 BC are still in use in tablets from 300 BC, a span of 7,800 years. The educational institutions preserved knowledge across the rise and fall of empires, across changes in political power, across shifts in spoken language. What they didn't preserve, or didn't record, was the origin of the knowledge itself. We have no tablet that says, in the reign of King X, the mathematician Y discovered method Z. We have no legends of mathematical heroes, no myths of divine revelation of geometry. The knowledge simply exists, integrated into the curriculum, part of what every educated scribe knows. This anonymity is both frustrating and suggestive. Frustrating because we can't trace the development of ideas, can't identify individual contributors, can't construct a historical narrative of discovery. Suggestive because it implies the knowledge was seen as communal, inherited, traditional, not as recent innovation. When a Greek mathematician made a breakthrough, it was news. When Archimedes derived new methods for calculating volumes, people noticed. His work was preserved under his name, celebrated, attributed. When a Babylonian scribe calculated a new table of reciprocals or compiled a new set of problem texts, apparently no one thought to record who did it. It was just part of the work, part of the ongoing maintenance of knowledge, unless of course they weren't compiling new knowledge, unless they were copying, preserving, maintaining knowledge that already existed. The tablets from House F don't answer this question. They just show us what was taught. They show us the system worked, that knowledge was transmitted successfully across generations. They show us that in 1800 BC, scribal students in Nipper were learning sophisticated mathematics that would look impressive in a modern high school. But they don't tell us where that mathematics came from. For that, we need to ask a different kind of question. The base 60 question. Why 60? It's a strange choice for a number base. We use 10, probably because we have 10 fingers. Binary makes sense for computers. Hexadecimal 16 is convenient for computing. But 60? And yet the Sumerians chose it, or inherited it, somewhere around 3000 BC, and it stuck. For the next 3000 years, 60 was the foundation of Mesopotamian mathematics. It shaped their arithmetic, their algebra, their geometry. It determined how they measured time and angles, and we still live with that choice: 60 seconds, 60 minutes, 360 degrees. The usual explanation is that 60 is highly composite. It has many divisors. You can divide 60 evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20 and 30. This makes it ideal for working with fractions. If you're distributing grain to workers or calculating shares of a temple offering, a base with many factors simplifies the arithmetic. 10, by contrast, is divisible only by 2 and 5. Try to divide 10 by 3 and you get a repeating decimal. In base 10, 1/3 is 0.333 forever. In base 60, 1/3 is exactly 0,020. Clean, simple, finite. For a civilization doing complex administration, trade and astronomy, this matters. Base 60 reduces the number of unresolvable fractions, makes calculations cleaner, simplifies table construction. But does that fully explain why they chose it initially? Some scholars point to astronomy. The Sumerians were obsessive sky watchers, tracking the movements of the sun, moon and planets. The solar year is close to 360 days, not exactly, but close enough that a 360-day calendar with periodic adjustments was workable. Dividing the circle of the sky into 360 degrees and the day into 360-degree measures might have emerged from astronomical observation. But this raises a chicken and egg problem. Did astronomical observation lead to base 60, or did base 60 shape how they described astronomical observation? We don't know. The sexagesimal system is already in use in the earliest Sumerian mathematical texts we have from around 2500 BC. Its origins are pre-literate, lost in the centuries before writing stabilised enough to leave clear records, Another theory, finger counting. You can count to 12 on one hand by using your thumb to touch each of the 3 segments on your 4 fingers. 12 segments. Then use the fingers of your other hand to track how many 12s you've counted. 5 fingers times 12 is 60. So you can count to 60 using both hands in a systematic way. This is speculative, but it's not implausible. Many cultures have complex finger counting systems that extend well beyond 10. If such a system was culturally embedded in pre-literate Sumer, it might have been formalized into a written number system once writing developed. The problem with all these explanations is that they're post hoc. We're looking at the system as it exists and trying to reverse engineer why someone would design it that way. But cultural choices aren't always optimal. Sometimes systems persist because they're traditional, not because they're ideal. What if base 60 wasn't chosen at all? What if it was inherited? This is where the question becomes uncomfortable. If the sexagesimal system wasn't developed by the Sumerians, but was already in use when Sumerian civilization emerged, then it predates our earliest evidence of complex urban society in Mesopotamia. It pushes mathematics back into the Uruk period 4000, 3000 BC or earlier, into times we have almost no written records from, when we're working from archaeological remains and pottery sequences rather than texts. Or it suggests the knowledge came from elsewhere, transmitted from a culture we haven't identified or don't recognize as mathematically sophisticated. The conventional historical view is that complex mathematics emerges from a complex society. Civilization produces administration, administration requires record keeping develops into writing and mathematics. This is a bottom-up materialist explanation that fits the archaeological evidence. But the sexagesimal system doesn't feel emergent, it feels designed. Someone had to make a choice, let's use 60 as our base, and that choice shaped everything that followed. The entire edifice of Mesopotamian mathematics, the tables, the algorithms, the geometric calculations, is built on that foundation. If it was designed, by whom and when? The earliest numerical tablets from Mesopotamia from the late 4th millennium BC already show a complex system with different bases for different types of counting. Base 60 for abstract numbers, base 10 for some goods, base 12 for others, specialized systems for area and volume. This isn't a simple primitive counting system that gradually becomes more sophisticated. It's complex from the start. By the time we have clear textual evidence around 2500 BC in the early dynastic period, the system is fully formed and standardized. Mathematical tables exist. Scribes are being trained in computational methods. The infrastructure is already there. And here's where Plimpton 322 becomes relevant again. The tablet uses sexagesimal computation to generate Pythagorean triples and organize them by trigonometric ratios. The mathematics requires not just understanding the number system, but mastering it, computing multi-digit sexagesimal numbers accurately, maintaining precision across complex calculations, organizing results systematically. This level of competence doesn't emerge overnight. It represents generations of practice, refinement, teaching. By 1800 BC, when Plimpton 322 was made, the sexagesimal tradition was already ancient. The old Babylonian scribes who made tablets like Plimpton 322 were working within a mathematical framework at least 1,000 years old, possibly much older. Did they understand where it came from? Did they know who first chose base 60 or why? The tablets don't say. The knowledge is simply there, part of the inherited tradition, taught in schools, applied in practice, transmitted forward without commentary on its origins. This is the paradox at the heart of Mesopotamian mathematics. It's simultaneously sophisticated and anonymous, advanced and traditional, innovative in application, and conservative in preservation. Modern mathematics prizes originality. We name theorems after their discoverers. We track the development of ideas through publications and citations. We construct genealogies of knowledge. Ancient mathematics, at least as we see it in Mesopotamia, doesn't work that way. The emphasis is on preservation, on accurate transmission, on maintaining what is known rather than discovering what is new, unless they're the same thing, unless preserving and discovering point to the same reality from different angles, unless what the Mesopotamians were preserving was itself a discovery, but made so far back in times so remote that the discoverers' names were lost and the knowledge itself became tradition. The base 60 system endured for 3 millennia and influences us still. That's a remarkable legacy for a choice made in the 4th millennium BC or earlier. It suggests something important, that mathematical knowledge, once established, can persist across enormous spans of time if the institutions exist to transmit it. But it also suggests vulnerability. If the institutions fail, if scribal schools close, if tablets are no longer copied, if the educational system collapses, the knowledge can vanish within a generation or two, which is exactly what happened. By the 1st century AD, cuneiform was dying. The last dated cuneiform tablet is from 75 AD. After that, silence. 3,000 years of accumulated knowledge, mathematical, astronomical, literary, religious, became inaccessible. It took us 2,000 years to recover even a fraction of it, and some of what we've recovered has challenged our understanding of what the ancients knew, which brings us to Eleanor Robson, and a very different interpretation of Plimpton 322, when Robson read between the lines. In 2002, 57 years after Neugebauer's groundbreaking interpretation, Eleanor Robson published a paper titled Words and Pictures, New Light, on Plimpton 322. Robson, a British mathematician and historian of science specialising in Mesopotamian mathematics, offered a fundamental challenge to the trigonometry hypothesis. Her argument was simple and devastating. Context matters. Robson examined not just Plimpton 310.2 in isolation, but the entire corpus of Old Babylonian mathematical tablets. She looked at what other tablets from the same period contained, how they were organised, what purposes they served, and she concluded that Plimpton 322 didn't look like a reference table, it looked like a teacher's exercise set. Here's her reasoning. Most Old Babylonian mathematical tablets are problem texts. They pose questions. A rectangle has area 600 and diagonal 50. What are its sides? Then they give a step-by-step solution showing the algorithmic procedure a scribe should follow. These tablets are teaching tools, demonstrating methods. Some tablets are table texts, lists of multiples, reciprocals, squares or square roots. These are reference materials meant to be consulted during calculations or memorised by students. Plimpton 322 doesn't quite fit either category. It's not a problem text. There are no questions posed, no solutions shown. But if it's a reference table, it's a very strange one. The numbers are impractically large. The organisation is unusual. And crucially, it's incomplete. The missing left columns would have contained essential information if this was meant to be a functional reference. Robson suggested that Plimpton 3T2 is instead a teacher's aid, a collection of problems involving Pythagorean triples, organised by difficulty, with the numerical answers pre-computed so the teacher could check student work. The tablet would have been used alongside problem statements, perhaps written on a separate tablet or dictated orally, and students would work through the calculations to arrive at the answers shown. Under this interpretation, the sophisticated mathematics is still there, the Pythagorean triples, the precise calculations, but the purpose is pedagogical rather than practical. It's not a tool for surveyors or architects, it's a tool for teachers. This fits the archaeological context. Plimpton 322 was found in a collection that likely came from a scribal school environment. Other tablets from similar contexts are clearly educational. The size and format of Plimpton 322 match school tablets more than professional reference works. Robson's interpretation also addresses a puzzle Neugebauer couldn't explain. Why these specific 15 triples? If the tablet is a trigonometric table, you'd want even coverage across the range of angles. But the angles on Plimpton 322 cluster between 45 and 31 with no apparent systematic spacing. If, however, the tablet is a problem set, then the selection makes sense. These 15 problems represent a range of difficulties, from relatively straightforward calculations to quite complex ones. A teacher compiling exercises might choose triples that test different aspects of the student's skill without worrying about systematic angular coverage. Robson's paper was careful and well argued. It forced scholars to reconsider assumptions that had become entrenched over half a century, and it generated debate, which is exactly what good scholarship should do. Some mathematicians pushed back. They argued that the organisation by sec, the column I values, is too precise to be accidental. If this was just a grab bag of pedagogical examples, why would they be arranged in order of a specific trigonometric function? That ordering suggests purpose, intention, a underlying structure that goes beyond here are some problems for students. Others pointed out that reference table and pedagogical tool aren't mutually exclusive. A teacher's reference of problems is still a reference. Students consulting it would be learning relationships that they could apply elsewhere. The distinction Robson drew might be a difference in emphasis rather than kind. But the deeper question Robson raised is methodological. How do we interpret artifacts without explicit context? Plimpton 3222 doesn't have an instruction manual. It doesn't have a title page explaining its purpose. We have a clay tablet with numbers on it, and we're trying to reconstruct intention from structure. This is the challenge of all archaeology, all history. We have fragments, partial, ambiguous, separated from their original context by millennia. We build interpretations, narratives that make sense of the fragments. But multiple narratives can fit the same evidence. Choosing between them requires judgment, not just data. Robson's intervention was valuable because it reminded scholars not to overreach. Neugebauer's world's oldest trigonometric table interpretation was compelling and had become widely popularized. But popularization can ossify into dogma. Robson injected uncertainty, reminded the field that we don't know with certainty what Plimpton 322 was for. And yet the tablet remains remarkable regardless of its purpose. Whether it's trigonometry or pedagogy or both, it represents sophisticated mathematical thinking in the early 2nd millennium BC. The Pythagorean triples are real. The computational precision is real. The systematic organisation is real. What we don't know, what we can't know without finding more tablets, more context, more explicit commentary, is exactly how the Babylonians understood what they were doing. Did they conceptualize these relationships trigonometrically as angles and ratios, or purely algebraically as number relationships? Did they see the geometric meaning or just the arithmetic? The tablets are silent on these questions. They show the results, not the thinking. They demonstrate competence, not comprehension. But then, in 2017, two mathematicians took another look at Plimpton 322 and offered yet another interpretation, one that revived the trigonometry hypothesis in a new form, Mansfield and Weilberger's exact trigonometry. Daniel Mansfield and Norman Weilberger, both mathematicians at the University of New South Wales in Australia, published a paper in 2017 with an audacious title, Plimpton 322 is Babylonian exact sexagesimal trigonometry. Their argument combined historical analysis with a new mathematical framework called rational trigonometry, a reformulation of trigonometric relationships that avoids irrational numbers and works entirely with ratios of integers. Standard trigonometry, as we learn it in school, is based on angles and circular functions. You define sine, cosine, and tangent as ratios in a right triangle, or equivalently as coordinates on a unit circle. These functions output real numbers, often irrational, sin 30, lick 1/2, but sin 45, lick 1/2, an irrational number. This works fine for modern mathematics, where we're comfortable with irrational numbers and decimal approximations, but it's anachronistic for ancient mathematics. The Babylonians avoided irrational numbers. Their entire mathematical system was built on ratios of integers, on finite sexagesimal expansions, on calculations that terminated rather than repeating endlessly. Wildberger had spent years developing an alternative approach to trigonometry that eliminated irrationals entirely by working with squared ratios instead of ratios themselves. In his system, instead of computing sin, you compute sin, which for Pythagorean triples is always a rational number of r over n. When Mansfield and Wildberger examined Plimpton 322 through this lens, something clicked. The tablet wasn't using approximations or irrational numbers. It was doing exact trigonometry in a way perfectly suited to the sexagesimal system, a form of trigonometry that might actually be superior to the Greek approach for certain applications. Here's their key insight. Plimpton 322 uses Pythagorean triples to create a table of exact trigonometric values. Each triple, RBC, represents a right triangle. The ratios AC, BC, AB, and their squares are all rational numbers. These ratios are functionally equivalent to sine, cosine, tangent, and their squares, exact values, no approximations, no irrational numbers. Column Y on the tablet tracks sex, the squared secant of the angle opposite side A. This value decreases from row to row, as decreases from about 45 to 31. The tablet is ordered by this function, making it a table for looking up trigonometric relationships. But unlike Hipparchus's chord tables or any later Greek trigonometry, this system never requires approximating irrationals. Every value is exact. Every calculation terminates. The mathematics is elegant, rigorous, and practical. If Mansfield and Wildberger are correct, then the Babylonians developed a form of trigonometry 5,100 years before the Greeks, and in some ways it was more sophisticated, better suited to calculation, free of the approximation errors that plague irrational-based trig. The 2017 paper generated enormous media attention. Headlines proclaimed ancient Babylonian tablet predates trigonometry by 1,500 years and mathematics just got rewritten. The story went viral. People love narratives where ancient civilizations were more advanced than we thought. But the academic response was mixed. Some scholars, particularly mathematicians, found the interpretation compelling. The rational trigonometry framework makes sense of the tablet's structure in a way that respects Babylonian mathematical practices. It doesn't impose modern concepts anachronistically. It reconstructs a system that fits what we know about how they worked. Others, particularly historians, were more cautious. They pointed out that Mansfield and Wildberger's interpretation, like Neugebauer's before it, assumes the Babylonians thought in terms of angles and trigonometric relationships. But we have no text where a Babylonian scribe explicitly discusses angles or trigonometry. We're inferring their conceptual framework from numerical patterns. Eleanor Robson, responding to the 2017 paper, reiterated her pedagogical interpretation and noted that trigonometric table and collection of problem answers are not mutually exclusive. A teacher might compile a table of problems ordered by difficulty which correlates with angle size, and that compilation would look mathematically like a trigonometric table, even if that wasn't the conscious intent. The debate, in other words, is ongoing. Scholars are still arguing about what Plimpton 322 is, what it was for, and what it tells us about Babylonian mathematical thought. What's not in dispute is the mathematical content. The triples are there. The precise calculations are there. The sophisticated organisation is there. Whether we call it trigonometry or algebra or geometry, the old Babylonian scribes were doing advanced mathematics. And they weren't alone. Echoes across the ancient world. In 1930, the French mathematician and historian Paul Tannery made an observation that has puzzled scholars ever since. The Pythagorean theorem was known at an earlier time in India than in Greece. He was referring to the Shulba Sutras, ancient Indian texts concerned with the construction of ritual fire altars. These texts, composed sometime between 800 and 500 BC, contain explicit geometric knowledge, including a clear statement of what we call the Pythagorean theorem. The Bodhayana Sulba Sutra, the oldest of these texts, states, "The diagonal of a rectangle produces by itself both the areas which the two sides of the rectangle produce separately." Translate this into algebra: if the sides of a rectangle are a and b, and the diagonal is d, then d dugra plus b. This is the Pythagorean theorem, stated clearly, applied systematically. The Bodhayana Sulba Sutra dates to around 800 BC, earlier than any surviving Greek text that mentions the theorem. Pythagoras himself lived around 570–495 BC, at least 2 centuries after Bodhayana. The text doesn't just state the theorem, it uses it. It provides procedures for constructing squares of different sizes, for transforming a rectangle into a square of equal area, for doubling or halving the area of a square, all using rope constructions and geometric relationships that depend on the Pythagorean theorem. And there's more. The Bodhayana Sulba Sutra gives an approximation for 2. Increase a unit length by its third, and this third by its own fourth less its 34th part. This is the diagonal of a square of side 1. Translated into numbers, 1 plus 1 3 plus 1 3 4, 1 4 3 4 3 4, so 1.41421156, which is accurate to 5 decimal places. The actual value of 2 is 1.4142135, so the error is less than 0.002%. This is essentially identical to the accuracy achieved on the Babylonian tablet YBC 728. 2 cultures, separated by thousands of kilometers, both computing 2 to 5 decimal places using similar iterative methods: coincidence, independent discovery, or transmission of knowledge. The mainstream academic view is that similar problems produce similar solutions. Both Indian and Mesopotamian cultures needed to do surveying, construct buildings, lay out ritual spaces. Both developed rope-based construction techniques. The rope in Sulba Sutras is explicit. Mesopotamian surveying used measured chords. Both noticed that certain rope lengths produce right angles reliably. Both formalized these observations into mathematical procedures. Independent discovery is plausible. The Pythagorean theorem isn't a complex abstraction. It's a directly observable property of right triangles that anyone doing practical geometry might notice. Given enough time and enough cultures, multiple discoveries seem inevitable. But Abraham Seidenberg, examining the similarities in detail, wasn't satisfied with independent discovery. Writing in the 1960s and 1970s, he argued that the geometric knowledge in both traditions shows specific procedural similarities that go beyond what you'd expect from parallel development. Both traditions use rope constructions to create geometric figures, apply the Pythagorean relationship in similar ways, show knowledge of Pythagorean triples, compute square roots using similar iterative algorithms, frame geometric knowledge as inherited sacred knowledge tool in India, scribal tradition in Mesopotamia. Seidenberg suggested 3 possibilities. Mesopotamia learned from India. India learned from Mesopotamia. Both learned from an earlier common source. The chronology makes option 1 unlikely. Mesopotamian evidence predates Indian evidence by 1,000 years. Option 2 is possible. There was trade contact between Mesopotamia and the Indus Valley civilization from at least the 3rd millennium BC. Mathematical ideas could have travelled along trade routes. But Seidenberg was intrigued by option 3. If both traditions show knowledge that seems fully formed at its earliest appearance, if neither tradition shows a clear developmental sequence from simple to complex, then perhaps both inherited the knowledge from somewhere earlier. This is where the hypothesis becomes controversial. An earlier common source for advanced mathematics pushes knowledge back into the 4th millennium BC or earlier, into periods for which we have minimal written evidence. It implies mathematical sophistication in cultures we don't usually think of as mathematically advanced. Most historians reject this. The absence of evidence isn't evidence of absence, but it's also not a license to invent hypothetical advanced civilizations. The safer interpretation is that mathematical knowledge developed gradually in both Mesopotamia and India, and our evidence captures moments in that development, not the beginning. But the pattern Seidenberg identified is real. Mathematical knowledge in both traditions presents itself as inherited, traditional, sacred even. It's not framed as recent discovery, but as ancient wisdom, preserved and transmitted by specialists. In Mesopotamia, that specialist class was scribes. In India, it was the Brahmin priests who composed and transmitted the Vedic texts. Both groups saw themselves as custodians of knowledge, not innovators. Compare this again with Greece. When Euclid compiled the Elements around 300 BC, he was consolidating discoveries made by Thales, Pythagoras, Eudoxus, and others, mathematicians whose names were remembered and celebrated. Greek mathematics had heroes. Mesopotamian and Indian mathematics had traditions. This difference in how knowledge is framed might tell us something about how it was understood. If you see mathematics as discovered truth, you celebrate the discoverers. If you see it as inherited wisdom, you honour the transmission. The irony is that we don't know which view is more accurate. Was the Pythagorean theorem discovered independently multiple times by different cultures? Or was it discovered once, far back in prehistory, and transmitted through various channels to Mesopotamia, India, and eventually Greece? The physical evidence, tablets like Plimpton 322, YB 7289, and IM 67118, texts like the Shulba Sutras, proves that the knowledge existed. It was sophisticated, systematic, and widely applied. What we can't prove is its origin. And that brings us to the most interesting question of all: what was on the missing columns of Plimpton 322? What the missing columns knew? Return to Columbia University's Rare Book Library. Look at Plimpton 322 again. The broken left edge is irregular, suggesting the break was accidental, perhaps during excavation, perhaps centuries earlier while buried. The surviving portion shows 4 columns, but the tablet's width and the spacing of the columns suggests there was room for at least 1 more column, possibly 2. What was written there? Scholars have attempted reconstructions. The most common theory, following Neugebauer, is that the missing column or columns contained the values, the short sides of the Pythagorean triples. Column 2 gives B, column 3 gives Sic, so A would complete the set. If that's correct, then the missing left portion would have listed row 1, 120, row 2, 3456, row 3, 4800, row 4, 13500, and so on. Having all 3 values explicitly shown would make the tablet more useful as a reference. Whether for trigonometry or pedagogy, you could read off complete triangles without needing to calculate the missing side. But there's a problem with this reconstruction. It assumes the tablet was meant to be used for looking up triangle sides. If that's the purpose, why organise by sec in column 1? That column becomes redundant if the goal is just to list triples. Mansfield and Wildberger suggest column I was the primary purpose. It's a table of trigonometric ratios, with the specific triples serving as examples that generate those ratios. The missing column might have contained different information, perhaps labels for the problems, or additional computed ratios, or even textual notes. Eleanor Robson's pedagogical interpretation suggests the missing column might have held the problem statements themselves. A rectangle has area x and diagonal y. Find the sides. The surviving columns would then be the answers, pre-computed for the teacher's reference. We don't know. The missing columns are gone, and with them, any explicit indication of purpose that might have been there. But the missing columns represent something larger, the incompleteness of our knowledge. We have fragments of ancient mathematics, tablets, texts, procedures. We can analyse them, translate them, interpret them, but we're missing the context, the instruction manual, the commentary that would tell us how the ancients understood what they were doing. Imagine if someone 3,000 years from now found a page from a calculus textbook. just the page with integral tables. No title, no introduction, no worked examples, just columns of functions and their integrals. They could probably figure out that it's mathematics. They might recognize some of the relationships, but would they understand what calculus is for? Would they grasp the concept of limits, derivatives, integration? Would they know whether this was a reference table for engineers, or a study guide for students, or an artifact of some cultural ritual? That's our situation with Plimpton 3122. We have the numbers, we can see the patterns, but the full context, intellectual, cultural, practical, is missing. And yet certain conclusions seem inescapable. First, the mathematics on Plimpton 322 is sophisticated. It requires understanding Pythagorean triples, knowing how to generate them systematically, being able to compute multi-digit sexagesimal numbers accurately, and organising results according to some principle, whether trigonometric, pedagogical, or otherwise. Second, this sophistication was not unique to Plimpton 322. Dozens of other Old Babylonian mathematical tablets demonstrate similar capabilities. YBC 7289, IM 67118, the mathematical problems from Nippur, the tables from they all show a mathematical culture operating at a high level. Third, this high level of mathematical competence appears early in the documentary record. We don't see a gradual progression from simple to complex. By the time we have extensive written evidence, around 2000 BC, the mathematics is already advanced. Fourth, similar mathematical knowledge appears in India in the Shulba Sutras several centuries later. The similarities are specific enough to suggest some form of transmission or common origin, though independent discovery remains possible. Fifth, when Greek mathematics emerged, it showed awareness of these earlier traditions. Thales reportedly studied in Egypt. Pythagoras was said to have travelled to Babylon. Whether these legends are historical or symbolic, they reflect an ancient understanding that mathematical knowledge had Near Eastern roots. Now, three interpretations are possible. Interpretation 1, the standard view. Mathematical knowledge developed gradually in response to practical needs. The Sumerians developed base 60 for administrative reasons. Scribes refined computational methods over generations. By the Old Babylonian period, accumulated techniques had reached a high level of sophistication. Plimpton 322 represents the peak of this development, a culture doing complex mathematics because it had built the institutional infrastructure calls, standardized curriculum, durable writing medium to support it. Under this view, the mathematics is impressive but not mysterious. It's the product of human intelligence applied to practical problems over long time spans. The Greeks later developed their own mathematical tradition, influenced by Near Eastern predecessors, but fundamentally independent in its approach, emphasis on proof rather than algorithm. This interpretation is parsimonious, fits the archaeological evidence, and doesn't require any additional hypotheses. Interpretation 2, the transmission view. Mathematical knowledge was discovered earlier than our evidence suggests, perhaps in the 4th millennium BC or even earlier, and transmitted through scribal and priestly lineages. The knowledge preserved in tablets like Plimpton 322 is not recent innovation, but the continuation of a much older tradition. The Sumerian sexagesimal system, the algorithmic methods, the geometric insights, these were inherited from previous generations, copied and maintained by scribes who saw themselves as preservers rather than creators. The knowledge eventually spread beyond Mesopotamia, reaching India and influencing the development of Greek mathematics. Under this view, the sophistication of Old Babylonian mathematics is explained by its being old, not recent invention, but accumulated and refined knowledge from earlier phases of human civilization. This interpretation explains why mathematical procedures appear fully formed in the earliest texts. It accounts for the scribal culture's emphasis on transmission and preservation. It fits the way ancient sources themselves frame knowledge as inherited wisdom, but it pushes the origin of advanced mathematics back into periods with less evidence, requiring us to accept that cultures we know less about were more capable than we might assume. Interpretation 3. The common source view. Following Seidenberg, perhaps Mesopotamian and Indian mathematics both descend from an even earlier tradition, a Neolithic or Chalcolithic culture that developed sophisticated mathematical ideas for reasons we can't reconstruct. This hypothetical source culture would have predated Sumerian civilization, existing in the 5th or 6th millennium BC or earlier. This interpretation is the most speculative. It requires assuming a high level of mathematical competence in cultures for which we have no direct evidence of such knowledge. It's unfalsifiable. The absence of evidence becomes evidence of loss rather than evidence of absence. Most historians reject this interpretation as too speculative, but it's worth noting that it's not impossible. Complex knowledge can exist in cultures that leave little material trace. Mathematics doesn't require monumental architecture or metal tools. It requires curiosity, time, and a way to transmit ideas. Oral traditions can preserve complex information for generations before writing emerges. Which interpretation is correct? We don't know. We may never know. The evidence is fragmentary. The missing columns of Plimpton 322 mirror the missing evidence from history itself, the countless tablets lost, the oral traditions unrecorded, the knowledge forgotten when civilizations collapsed. What we can say is this: the mathematics existed. By 1800 BC the Babylonians had it, by 800 BC the Indians had it, by 300 BC the Greeks had it and were developing it further. The torch was passed. Knowledge persisted. But where the torch was first lit, that remains in shadow. The inheritance waiting in the clay. Night has deepened outside the rare book library. The temperature-controlled air hums softly. Behind glass, under carefully calibrated lighting, Plimpton 322 sits as it has sat for decades, silent, patient, holding its secrets in the wedge-shaped impressions pressed into River Clay 30 700 years ago. The tablet has outlasted the city that made it. Lhasa is ruins. The scribal schools are dust. The Euphrates has changed course. Empires have risen and fallen. Languages have lived and died. And through all of it, the mathematics remains, locked in fired clay, waiting for minds equipped to read it. Otto Neugebauer saw trigonometry. Eleanor Robson saw pedagogy. Daniel Mansfield and Norman Wildberger saw exact sexagesimal methods. Perhaps they're all correct. Perhaps the tablet was many things: a teaching tool that happened to organise trigonometric relationships, a reference table used in education, a demonstration of computational skill that preserved practical knowledge. Or perhaps what they're all seeing is the same thing from different angles, evidence of inheritance. The Babylonians didn't claim to have invented the mathematics on Plimpton 322. They don't attribute it to any individual. They present it as standard knowledge, part of what an educated scribe knows, transmitted through formal schooling from teacher to student across generations. The Indian mathematicians who composed the Shulba Sutras framed their knowledge similarly, as inherited wisdom, passed down from ancient rishis, preserved in ritual context because it was too important to lose. The Greeks, when they developed mathematics, looked east. Thales studied in Egypt. Pythagoras allegedly travelled to Babylon. Whether or not these stories are literally true, they reflect an awareness that mathematical knowledge had roots in older civilizations. What if that awareness was accurate? What if the mathematics we see flowering in Greece, the theorems we attribute to Pythagoras and Euclid and Archimedes, were extensions of a framework inherited from Mesopotamia and Egypt? And what if the Mesopotamian and Egyptian mathematics were themselves extensions of something older still? This is not a claim of lost advanced civilizations or ancient astronauts. It's a simpler observation. Knowledge compounds. Mathematics builds on itself. Each generation inherits what the previous generation discovered, preserves it, transmits it, and occasionally adds to it. Most of human history is invisible to us. Writing is only 5,000 years old. Anatomically, modern humans have existed for 200,000 years. For 97% of that time, we have no written records at all. We know people were behaviourally sophisticated, they created art, music, burial rituals, symbolic thought. Did they also create mathematics? They counted. That much is clear from notched bones and carved marks dating back tens of thousands of years. They recognised patterns. Astronomy is as old as human culture. Every society tracks the moon and stars. They solved spatial problems, building shelters, crafting tools, navigating landscapes, all require geometric intuition. At some point, someone formalised that knowledge. Someone realised that right triangles have predictable relationships. Someone discovered you could generate those relationships systematically. Someone developed methods for calculation and ways to teach those methods to others. We don't know who, we don't know when, we don't know where. What we know is that by the time writing becomes common enough to leave abundant records, the knowledge already exists. The mathematics on Plimpton 322 isn't primitive, it isn't crude, and it isn't experimental. It's refined, it's sophisticated, it's the product of a long tradition. The broken left edge of the tablet is a fitting metaphor. We can see part of the picture. We can analyse what's there, translate the numbers, identify the patterns, but we can't see what's missing. The complete picture, the full context, the origins, the chain of transmission reaching back into prehistory is gone. And yet the mathematics itself survives, transferred from clay to paper, from cuneiform to our notation, from ancient Lhasa to modern classrooms. The relationships remain true. A right triangle with sides in the ratio 3045 works the same today as it did in 1800 BC. The Pythagorean theorem holds across millennia. The base 60 system we inherited from measuring time and angles functions as reliably now as it did for the Sumerian astronomers who developed or inherited it. Knowledge, when properly encoded and transmitted, can outlast civilizations. But transmission is fragile. It depends on institutions, schools, libraries, universities that preserve and teach. It depends on media, clay tablets, paper, digital storage that resist decay. It depends on continuity, teachers teaching students who become teachers who teach the next generation. Break any link in that chain and knowledge vanishes. The 3,000-year silence of cuneiform proves it. From 75 AD to the 1850s, the mathematics on Plimpton 322 was inaccessible, locked in a script no one could read. The tablet existed, but the knowledge didn't. Information without interpretation is just noise. We've recovered some of what was lost. We can read cuneiform again. We can appreciate Babylonian mathematics on its own terms. We can trace the transmission of ideas from Mesopotamia to Greece, to the Islamic Golden Age to Renaissance Europe, to the modern world. But we can't recover what was never written down. Oral traditions, unless written, die with their last speaker. Practical knowledge, unless formalised, disappears when the practices change. The mathematical insights of Neolithic surveyors, of Sumerian astronomers before writing, of unknown teachers who first realised the patterns, all of this is gone. Unless it's not entirely gone, unless it's preserved in the traditions that followed, in the methods that were transmitted, in tablets like Plimpton 322 that crystallised knowledge at a particular moment in the long chain of human understanding. The tablet sits in its case. The numbers haven't changed in 3,700 years. The Pythagorean triples are still perfect. The sexagesimal notation still decodes to precise values. The mathematics works. The question isn't whether the Babylonians were sophisticated. They demonstrably were. The question is, how far back does that sophistication reach? How much of what we credit to historical civilizations was actually inherited from earlier times? We don't know. Perhaps we'll never know. Perhaps future excavations will uncover earlier evidence, or new analytical methods will extract more information from tablets already found. Perhaps the answer is buried in tells that haven't been excavated, in collections that haven't been studied, in tablets whose significance hasn't yet been recognised. Or perhaps the answer is simply this: human beings have always been intelligent. Our ancestors 10,000 years ago had brains identical to ours. They were capable of the same insights, the same creativity, the same logical reasoning. They lacked our accumulated knowledge, our institutional support, our technology, but they didn't lack intelligence. Given time and curiosity, what might they have discovered? What patterns might they have noticed? What knowledge might they have preserved in ways we can't detect? The mathematics on Plimpton 322 is a message from the past. It says, we were here, we understood, we calculated, we preserved what we knew so that future generations, your generation, could build on it. That message has reached us, transmitted across 37 centuries, preserved in a medium as simple as mud and as durable as stone. The torch has been passed, the inheritance waits, the questions remain open. What will we pass forward? What will future generations discover in what we preserve? And what knowledge, from times more ancient than we can trace, has shaped everything we think we discovered ourselves? The tablet has no answers, it only has numbers, and numbers, precise and patient, waiting to be read. Outside, the world continues. But in this climate-controlled room, for a moment, time collapses. The scribe in Lhasa and the scholar in New York are connected by mathematics, by the same relationships, the same patterns, the same truth, written in different scripts. The broken edge remains broken. The missing columns remain missing. The mystery endures. And perhaps that's appropriate. Perhaps the most important knowledge is the knowledge that there's more to know, that our understanding is incomplete, that our narratives are provisional, that the past holds secrets we've only begun to uncover. Sleep well. Let the questions settle gently. Somewhere in the accumulated wisdom of millennia, somewhere in the clay tablets and stone inscriptions and oral traditions, lost and recovered, lies the story of how we became who we are. Plimpton 322 is one page in that story, a page with numbers, precisely calculated, carefully preserved, waiting across centuries. What other pages remain unread?